Pick up any small object near you, a coin, a pen, a glass. Hold it for a moment and notice that it stays exactly as it is. It does not shrink, it does not spread across your hand, its edges remain where they are, and its weight remains steady. This feels completely ordinary, and that is precisely why it is worth pausing on. Because that stability, that quiet insistence on remaining itself, is not something the object is doing passively. It is the result of an arrangement happening deep inside it, at scales so small that no instrument you could hold would come close to resolving them. Every solid thing around you is made of atoms. You already know this, but knowing it and feeling what it implies are different things. An atom is mostly empty space. Its electrons move through a region vastly larger than anything at the center. If you scaled an atom until its outermost electron cloud filled a large room, the central region, the part responsible for almost all of the atom's mass, would be roughly the size of a grain of sand suspended in the middle of that room. Everything else would be open space. The grain of sand is the nucleus, and that grain is where almost everything that matters about the atom's identity is stored. The nucleus gives the atom its mass. It gives the atom its charge. It determines which element the atom is, and therefore which molecules it can form, which reactions it can participate in, and what role it plays in the physical world. The electrons respond to it. Chemistry happens around it, but the nucleus itself sits at the center and under ordinary conditions does nothing visible at all. It simply persists. That persistence is the question hiding in plain sight. The nucleus is unimaginably small, yet it holds together across the entire lifetime of most atoms, which can be billions of years. It contains particles that carry the same type of electrical charge, which means they repel one another with a force that grows stronger the closer they are pressed together. And yet, they remain pressed together. Something is keeping them there, and that something is operating in a regime where our everyday intuitions about matter, force, and even identity begin to lose their usual meanings. What is the nucleus actually made of? The question sounds simple. Protons and neutrons, you might say. And that answer is correct as far as it goes. But the moment you ask what those are made of, and what holds them together, and where the nucleus actually gets its mass, and why it has the charge it does, the answer descends into a structure that is genuinely strange. Strange in a precise, measurable, experimentally confirmed way. What force is strong enough to overcome electrical repulsion at those distances? If protons and neutrons are themselves made of something smaller, what holds those pieces together? And why does the mass of the nucleus seem to come from something other than the mass of its parts? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you are watching from, and if there is something about the universe you find yourself wondering about, share it with us in the comments. With that said, let's get back to the topic. The nucleus is small enough that quantum physics governs everything inside it, and quantum physics at that scale produces behavior that has no parallel in ordinary experience. To understand what the nucleus is made of, we have to follow the question inward, layer by layer, until we reach a place where the answer is no longer about particles at all. The grain of sand suspended in that enormous room carries almost the entire mass of the atom. Not some of it, almost all of it. The electrons contribute so little to the total mass that for most purposes they are simply ignored in the accounting. Everything substantial about matter, in terms of mass, is concentrated in that central point. To feel what this means, consider what density actually implies. Density is not just a number describing how tightly packed something is. It is a statement about which rules apply. Water and air obey the same basic physics, but their different densities mean they behave in completely different ways under pressure, under heat, under flow. The rules do not change, but the regime does. And in different regimes, different aspects of those rules become dominant. The nucleus exists in a regime unlike anything else we encounter. If you took the density of nuclear matter and applied it to something the size of a sugar cube, that cube would outweigh every mountain on Earth combined. This is not an approximation. Nuclear matter is so dense that ordinary concepts like surface, texture, and rigidity become meaningless at that scale. The nucleus is not a miniature solid object. It is matter compressed into a state where the physics of the everyday world simply does not apply. This density is the first thing that forces a different set of rules into play. At the scale of atoms and molecules, the forces governing behavior are electrical. Electrons interact with nuclei through electromagnetic attraction, and atoms interact with each other through the electrical fields of their electron clouds. These forces are well understood, and they operate comfortably across distances ranging from atomic scales up to everyday human scales and far beyond. But inside the nucleus, the distances between particles are so small that electromagnetic physics alone cannot account for what is observed. If you tried to calculate whether the nucleus could hold together using only electrical forces, the answer would be immediate and absolute. It could not. The repulsion between protons packed into that volume would be overwhelming. The nucleus, by the logic of electromagnetism alone, should not exist. And yet here it is. Here everything is. Every atom in every object you have ever touched contains a nucleus that has remained intact, often for timescales longer than the age of the solar system. The gap between what electromagnetism predicts and what is actually observed is not small, it is total, which means something else is operating inside the nucleus, something that does not appear at larger scales, something that only becomes relevant when matter is compressed to this extraordinary degree. The density of the nucleus is therefore not just a curious fact about how small things are. It is the reason a completely different physical interaction must exist. The nucleus is dense enough to require it, and the properties of that interaction, once examined, turn out to be unlike anything that governs the world we can see directly. This is the first layer the question requires. Before asking what the nucleus is made of in terms of particles or fields, we have to establish that the nucleus occupies a physical regime where new rules dominate. The scale is not merely smaller, it is categorically different, and in that different category, the behavior of matter changes in ways that will determine everything that follows. Protons carry positive electrical charge. This is one of the most precisely confirmed facts in physics, and positive charges repel one another always, with a force that follows a clean and well-tested relationship. The closer two positive charges are pressed together, the stronger that repulsion becomes. At ordinary distances, this repulsion is manageable. At atomic distances, it is significant. At nuclear distances, it is ferocious. To feel the scale of what this means, consider that protons inside a nucleus are separated by distances roughly 100,000 times smaller than the atom itself. The electrical repulsion between two protons at that separation is not a gentle push. It is an intense, continuous force driving them apart, with everything electromagnetism can deliver at that range. And inside a nucleus, there are multiple protons, all repelling one another simultaneously. A helium nucleus contains 2 protons, an oxygen nucleus contains 8, an iron nucleus contains 26, a uranium nucleus contains 92. In every case, all of those protons are confined within a region of essentially the same scale. As the number of protons increases, the total electrical repulsion inside the nucleus grows substantially. Every proton is pushing against every other one all the time. Neutrons do not carry electrical charge, which means they do not contribute to this repulsion. This already tells us something. Neutrons are present inside nuclei in numbers that roughly track the number of protons, and in heavier nuclei they actually outnumber the protons. Their presence is not accidental. They are doing something structurally necessary. A nucleus made only of protons would fly apart before it could be said to exist. The neutrons are part of what makes the arrangement possible, but neutrons alone cannot explain stability. They carry no charge, so they do not add repulsion, but they also cannot cancel the repulsion that the protons generate. Something must be actively holding the protons together despite the force driving them apart. And whatever that something is, it must be stronger than electromagnetism at these distances, because electromagnetism at these distances is already operating at its maximum intensity. This is the constraint the question imposes. The force responsible for nuclear stability must be capable of overwhelming one of the four fundamental interactions of nature within the nuclear volume. It must operate between protons, between neutrons, and between protons and neutrons. It must be strong enough to win decisively against electrical repulsion when particles are this close together. Neutrons also feel it, which means this force does not care about electrical charge. It responds to something else entirely, something that both protons and neutrons possess regardless of their charge. Whatever that property is, it is not one that appears in everyday physics. It belongs entirely to the nuclear regime, and its existence is demanded by the simple fact that nuclei are stable at all. The next layer of the question is therefore not about what the nucleus contains, but about what kind of force could possibly be responsible for holding it together. And the answer to that question carries a property so unusual that it immediately raises a further question about why nuclei have any upper size limit at all. Something holds the nucleus together. That much is required by the fact that nuclei exist. The force responsible has a name, but the name matters less than its behavior, because its behavior is what determines the structure of everything inside the nucleus, and everything the nucleus can become. At nuclear distances, this force is far stronger than electrical repulsion. It acts between protons and protons, between neutrons and neutrons, and between protons and neutrons. It does not distinguish between them in this regard. Whatever property it responds to, both types of nucleon carry it equally. This already sets it apart from electromagnetism, which responds only to charge and therefore treats protons and neutrons very differently. But the defining feature of this force is not its strength, it is its range. Unlike gravity and electromagnetism, which extend across all distances and simply weaken gradually as separation increases, this force drops away with extraordinary speed once particles move beyond a certain separation. That separation is roughly the diameter of a proton itself. Move two nucleons just slightly beyond that distance, and the force between them becomes negligible almost immediately. This behavior has a consequence that shapes the entire nucleus. Each nucleon can only feel the binding force from its immediate neighbours. A proton on one side of a large nucleus has essentially no direct binding interaction with a proton on the opposite side. The force simply does not reach that far. In contrast, the electrical repulsion between those same two protons does reach across the entire nucleus, because electromagnetism has no such cutoff. Inside a small nucleus, this asymmetry is manageable. Every nucleon is close enough to every other one that the short-range binding force operates effectively throughout. The nucleus is compact enough that the force covers the whole volume. Electrical repulsion is present, but the binding force wins decisively everywhere it acts. As a nucleus grows larger, the situation shifts. Adding more protons increases the total electrical repulsion throughout the entire volume. but adding more nucleons only extends the binding force locally. Each new nucleon bonds with its neighbours, but contributes repulsion that is felt everywhere. At some point, these two effects reach a balance, and beyond that point, adding more protons makes the nucleus progressively less stable. This is why there is an upper limit to how large a nucleus can be while remaining stable. It is a direct consequence of the range limitation of the binding force. The force is powerful but short-sighted. It can only hold what it can directly touch, and as the nucleus grows, the electrical repulsion accumulates faster than the binding force can compensate. This range limitation also explains why neutrons become increasingly important in heavier nuclei. Neutrons contribute binding force without adding electrical repulsion. They act as a kind of structural support, extending the reach of cohesion without worsening the electrical balance. But even this compensation has limits, which is why the heavier stable nuclei contain significantly more neutrons than protons, and why beyond a certain size, no stable configuration exists at all. The force that holds the nucleus together is therefore defined as much by what it cannot do as by what it can. Its strength is real and overwhelming at short range, but its inability to act across larger distances is what gives the nucleus its finite size, its preferred compositions, and ultimately its boundary conditions. And once that boundary is understood, the next question becomes unavoidable. If protons and neutrons are the components the force acts between, what are protons and neutrons actually made of? A proton sits inside the nucleus and behaves, from the outside, like a compact object with a fixed charge and a fixed mass. It responds to forces. It occupies a position. It contributes to the nucleus's overall properties in ways that can be measured with great precision. For a long time, this was enough. The proton was treated as a fundamental constituent, a smallest unit, something that did not require further explanation. That picture held until experiments began probing the proton directly, not by observing what it did from a distance, but by firing other particles into it at high energy and watching how those particles scattered. A solid, uniform object scatters incoming particles in a predictable, smooth way. The proton did not do that. The scattering patterns revealed something unexpected. The incoming particles were sometimes deflecting at large angles, as though they had struck something small and hard, buried inside the proton rather than passing through a diffuse uniform charge. This is the same logic used to reveal atomic structure decades earlier, when particles fired at a thin sheet of material occasionally bounced directly backward, indicating that mass was concentrated in a tiny central region rather than spread evenly. The proton, subjected to similar scrutiny, revealed the same signature. It had internal structure, it was not elementary. What lives inside the proton are smaller constituents bound together in an extremely compact region. The neutron contains them as well. These constituents carry fractional electrical charges, meaning charges that are fractions of the proton's total charge, which add up to produce the whole. The proton's charge and the neutron's near-zero charge both emerge from how these internal charges combine. 3 of these constituents reside inside each nucleon, arranged in a configuration that quantum rules govern completely. This matters for the question of what the nucleus is made of, because it pushes the answer one level deeper. The nucleus contains protons and neutrons, but protons and neutrons are themselves composite. They have an inside. They are not the bottom of the structure, which means the nucleus, when examined at sufficient depth, is not made of protons and neutrons in the way a wall is made of bricks. It is made of something more fundamental that protons and neutrons are themselves expressions of. The internal constituents of nucleons are confined so tightly that the space they occupy is smaller than the proton itself by a significant margin. They move within that space, and their motion is not calm or slow. They are in a state of constant, rapid quantum activity, their positions and momenta governed by uncertainty in the most literal physical sense. The proton's interior is not a static arrangement, it is a dynamic, perpetually active quantum system. This internal activity has a consequence that becomes central to the next layer of the question. If you add up the masses of the three internal constituents of a proton, the total falls far short of the proton's actual mass. The constituents account for only a small fraction of what the proton weighs. The rest of the mass comes from somewhere else entirely, and identifying that source is what the next step requires. The three constituents inside a proton have masses that can be estimated. When those estimates are added together, the result is a small fraction of the proton's total measured mass. Depending on how the calculation is approached, the constituents account for somewhere around 1% to a few percent of what the proton actually weighs. The rest, the overwhelming majority of the proton's mass, comes from something other than the mass of its parts. This is worth sitting with for a moment. The proton is one of the most stable and precisely measured objects in physics. Its mass is known to extraordinary accuracy, and yet, if you tried to build a proton's mass from the masses of its constituents, you would fall almost entirely short. The ingredients do not add up to the product. Something else is contributing, and that something else carries almost all the weight. The same is true for neutrons. Their internal constituents have similar masses to those inside protons, and the same accounting problem appears. The neutron weighs far more than its parts would suggest, and since nucleons make up essentially all of the mass of every nucleus, and nuclei make up essentially all of the mass of every atom, this means that almost all of the mass of everything you can see and touch comes from this unaccounted portion. What fills the gap is not matter in the usual sense, it is energy. Specifically, it is the energy of the field that binds the constituents together, and the energy of the constituents' own motion within the confined space they occupy. Both of these contributions are enormous relative to the rest mass of the constituents themselves, and both arise directly from the extreme confinement the constituents experience inside the nucleon. The connection between energy and mass is not a metaphor here. It is a precise physical equivalence. Energy has mass. A system that contains a large amount of internal energy weighs more than one that contains less, even if the number and type of particles inside are identical. The proton is heavy because its interior is energetically intense. The confinement creates motion, and that motion contributes mass. The binding field stores energy, and that energy contributes mass. This reframes what the nucleus is made of in a fundamental way. When you hold something solid and feel its weight, you are feeling mostly the consequence of confinement and field energy operating inside nucleons. The matter you are touching is heavy, primarily because of how forcefully its internal constituents are held together, not because those constituents themselves are massive. The constituents are light, the binding is intense. The intensity of the binding is what produces the mass, and understanding why the binding is so intense and why it produces mass, rather than simply holding particles in place, requires looking directly at the field responsible. That field behaves in a way that has no parallel anywhere else in known physics, and its most important property is one that seems at first to violate every expectation built from ordinary experience. Every force familiar from daily experience weakens as distance increases. Gravity pulls less strongly as objects move apart. Electrical attraction fades as charges separate. Even the short-range nuclear force between nucleons drops away rapidly once separation grows. This weakening with distance feels like a basic feature of how forces must work, so natural that it barely seems worth stating. The field binding the constituents inside a proton does the opposite. As the constituents move apart from one another, the force pulling them back together grows stronger. At very close range, inside the nucleon, the constituents actually move with considerable freedom. The binding force at short distances is relatively relaxed, allowing them to shift and move within the confined volume without strong resistance. But as separation increases, the force intensifies. The further apart they move, the harder the field pulls them back. To build an intuition for this, consider a rubber band stretched between 2 points. At small separations, the tension is low and the band moves easily. As the separation grows, the tension rises. Pull far enough and the resistance becomes substantial. The field inside the nucleon behaves with a similar logic, except that the scaling of the force with distance is far more extreme, and unlike a rubber band, it never simply snaps. The field does not break. This behavior arises because the field itself carries the property that makes it interact. Unlike the electromagnetic field, which is generated by charged particles, but does not itself carry charge, the field binding the constituents inside nucleons carries the equivalent of its own source. This means the field interacts with itself. As it stretches between separating constituents, it does not thin out and weaken. It draws additional field energy into the gap, reinforcing itself, maintaining and increasing its pull. The energy stored in the field between separating constituents therefore grows as they move apart. Pulling two constituents away from each other requires continuously adding energy to the system. The further the separation, the more energy is required. And because energy has mass, the system becomes progressively heavier as the constituents are pulled apart, not lighter as might be expected if the goal were to remove parts. At a certain point, the energy concentrated in the stretching field becomes large enough to do something that has no parallel in ordinary mechanics. The field contains enough energy to spontaneously produce a new pair of constituents. Rather than the original two separating freely, the energy of separation materializes as new matter, and what emerges is two composite objects rather than two isolated constituents. The field has converted its own energy into particles before allowing a free constituent to exist. This is why the constituents inside nucleons have never been observed in isolation. Every attempt to separate them results in new composite particles being created from the field's energy. The constituents are not trapped in the way a marble is trapped inside a box. They are confined in a more fundamental sense. The field's own behavior makes isolation physically impossible, and this impossibility is not a limitation of experiment. It is built into how the field operates. The behavior described in the previous layer has a name in physics, but the name matters less than what it means structurally. The constituents inside a nucleon cannot be extracted, not with more energy, not with stronger instruments, not with any conceivable experimental arrangement operating within the laws of physics as they are understood. Every attempt to remove a constituent from the nucleon produces new composite particles instead. The constituent remains confined always, without exception. This is a different kind of boundary than anything encountered elsewhere in physics. An electron can be removed from an atom if enough energy is supplied. The energy required is finite and well defined, and once supplied, the electron exists freely outside the atom. The atom has been ionized. The electron is separate. This is a genuine extraction, a real separation of a part from a whole. Nothing analogous happens inside a nucleon. There is no energy threshold beyond which a constituent emerges freely. The threshold does not exist because the mechanism of confinement does not weaken as energy increases. It responds to increasing energy by producing more matter. The field converts the input energy into new particles before a free constituent can form. Confinement is therefore not a cage that could in principle be opened with sufficient force. It is a property of how the field itself behaves under any conditions. This changes what it means to ask what the nucleus is made of. If the constituents of protons and neutrons can never exist outside them, then in a meaningful physical sense the proton and the neutron are the smallest freely existing objects at this level of structure. The constituents are real. Their properties are measurable through how they affect scattering patterns and other indirect signatures, but they do not exist as separate, isolatable objects. They exist only within the composite structures they form. The nucleus is therefore made of objects whose own constituents are permanently and inescapably bound. Every proton and every neutron inside the nucleus contains 3 constituents that will never appear outside it. The nucleus is not a collection of separable layers that could, in principle, be peeled apart down to some final irreducible piece. At the level of the constituents, separation is not a physical option. What confinement also means is that the energy inside the nucleon cannot be cleanly separated from the structure of the nucleon itself. The field energy, the motion energy of the constituents, and the mass of the nucleon are not 3 distinct things that happen to add up. They are the same physical reality described from different angles. The nucleon has mass because confinement forces the interior into an energetically intense state, and that intensity is inseparable from what the nucleon is. This has a further consequence for the nucleus as a whole. The protons and neutrons inside the nucleus are themselves objects whose identity is entirely maintained by internal confinement. They persist as protons and neutrons because their interiors remain confined. If that confinement were somehow suspended, the protons and neutrons would cease to exist as recognizable objects. The nucleus would not simply fall apart. It would dissolve into a state of matter where the boundary between one nucleon and another loses meaning entirely. That state has a name and has been produced under extreme conditions, but its existence points to something important. The nucleus is not just a collection of particles arranged in space. It is a structure whose components are themselves structures, maintained by a form of confinement that is absolute. And the mass that confinement produces inside each nucleon is what the next layer must account for precisely. The proton weighs what it weighs because its interior is in a state of extreme energetic intensity. The constituents move rapidly within a confined volume. The field binding them stores enormous energy in the gaps between them. Neither of these contributions comes from the rest mass of the constituents themselves. Both come from the dynamics of confinement, from motion, and from field energy operating in an impossibly small space. To feel why confinement produces energy, it helps to recall something from quantum physics that applies broadly. When a particle is confined to a small region, its momentum cannot be zero. Quantum rules forbid a particle from being both precisely located and perfectly still. The smaller the region of confinement, the larger the range of momenta the particle must have, which means the more energetically active it must be. Confinement and energetic intensity are not merely correlated. They are the same constraint expressed in 2 ways. Inside a nucleon, the constituents are confined to one of the smallest volumes known in physics. The quantum rules governing their motion therefore demand that they carry significant momentum at all times. They cannot settle into stillness. They cannot reduce their activity. The confinement itself forces continuous, intense motion, and that motion carries energy, and that energy has mass. The field contributes separately and substantially. As described in the previous layer, the field binding the constituents strengthens with distance and stores energy as it stretches. Even within the small volume of the nucleon, the field is constantly active, mediating interactions between constituents, carrying momentum between them, and holding the interior in a state of dynamic balance. The energy stored in that field activity adds to the nucleon's mass directly. What results is a nucleon whose mass is almost entirely made of two things: the kinetic energy of confined constituents and the energy of the field that keeps them confined. The constituents themselves contribute a small remainder. The nucleon is therefore not a heavy object containing light pieces. It is a light system of pieces whose confinement forces the whole to be heavy. This reframes the mass of ordinary matter at the deepest level currently understood. When you feel the weight of anything, you are feeling primarily the consequence of this confinement operating inside every nucleon, in every nucleus of every atom in the object. The heaviness of the world is not stored in tiny massive particles. It is stored in the energetic intensity of fields and motion operating at nuclear and subnuclear scales. There is a further consequence that connects directly to the nucleus as a whole. The mass of a nucleus is slightly less than the combined mass of its protons and neutrons measured separately. This difference, the mass defect encountered in earlier discussions of nuclear energy, reflects the binding energy of the nucleus itself. The nucleons inside the nucleus are in a lower energy state than they would be if separated, and that lower energy corresponds to lower mass. So the nucleus carries two layers of this same principle. Inside each nucleon, confinement produces mass from field energy and motion. Between nucleons, binding reduces mass by lowering the total energy of the system. Mass at the nuclear level is not a fixed property of particles. It is a running account of how much energy the system is carrying at each layer of its structure, and the quantum rules governing which energy states are available at each layer determine everything about how the nucleus is organized. The nucleus does not arrange its protons and neutrons the way marbles settle into a jar, filling available space according to geometry and gravity. The interior of the nucleus is a quantum system, and quantum systems do not work by filling space. They work by occupying states. Each state is defined by a precise set of properties, and the rules governing which states are available and how many particles can occupy each one determine the entire internal organization of the nucleus. The most consequential of these rules is one that applies to protons and neutrons specifically. Two identical particles of this type cannot occupy the same quantum state simultaneously. This is not a restriction imposed from outside by some external constraint. It is a fundamental feature of how particles with this class of quantum identity behave. Each proton must occupy a state that no other proton already occupies. Each neutron must do the same among neutrons. This forces the nucleus into a layered structure. As protons are added one by one, each new proton must find an unoccupied state. The lowest available states fill first. Once they are full, new protons must occupy higher energy states. The same process happens independently for neutrons. The nucleus builds upward through a sequence of energy levels, with each level holding a limited number of particles before the next must be used. This structure has immediate consequences for nuclear stability. A nucleus with protons and neutrons filling their respective energy levels in a balanced way sits in a lower overall energy configuration than one where the levels are filled unevenly. Nuclei where specific numbers of protons or neutrons complete particular groupings of energy levels are especially stable, measurably more so than their neighbors in the chart of nuclear compositions. These preferred numbers appear repeatedly across measurements of nuclear properties and reflect the underlying shell structure of the nucleus directly. The energy levels themselves are shaped by the forces operating inside the nucleus. The short-range binding force between nucleons, the electrical repulsion between protons, and the quantum rules governing motion within the confined nuclear volume all contribute to defining what states are available and at what energies. The nucleus is not a passive container holding particles in fixed positions. It is an active quantum system whose allowed states are continuously shaped by the interactions happening within it. Spin contributes another layer. Each nucleon carries an intrinsic quantum property that behaves like a small angular momentum. When nucleons pair within energy levels, their spins combine according to quantum rules. Nuclei with even numbers of protons and even numbers of neutrons tend to have their spins cancel in pairs, producing a nucleus with zero total spin. Nuclei with unpaired nucleons carry a net spin that reflects the quantum state of the unpaired particle. This spin is measurable and contributes to how the nucleus interacts with magnetic fields and with radiation. The charge of the nucleus follows similarly. Each proton contributes its charge, and the total charge of the nucleus is simply the sum. But the distribution of that charge within the nuclear volume and how it responds to external fields depends on the quantum state of the nucleus as a whole, on how the protons are arranged across the available energy levels, and how their wave functions overlap within the nuclear volume. The nucleus is therefore not defined by which particles it contains in the way a bag is defined by what is placed inside it. It is defined by which quantum states its particles occupy, how those states interact, and what total properties emerge from that occupation. Changing the quantum state of the nucleus, even without adding or removing particles, changes its energy, its spin, and its behavior. The nucleus is its quantum state, not merely its particle count. Something important has been quietly accumulating across the previous layers. The force that holds the nucleus together, the short-range binding force between protons and neutrons, has been treated as fundamental to the nuclear structure. It is what overcomes electrical repulsion. It is what sets the range limit on nuclear size. It is what makes the existence of nuclei possible at all. But once the interior of nucleons is examined, this force reveals itself to be something other than fundamental. It is a consequence of something deeper. The field binding the constituents inside each nucleon is the primary interaction. It operates between the constituents directly, holding them inside the proton or neutron with the intense distance strengthening grip described earlier. This field acts on the constituents and on itself, and under ordinary conditions its effects are entirely contained within the nucleon. The nucleon presents a neutral face to the outside world in terms of this interaction, in the same way that a neutral atom presents a near-zero electrical face to distant objects, despite containing charged particles inside. But the containment is not perfect. Just as the electrical fields of a neutral atom are not completely cancelled at very close range, producing the weak residual attractions responsible for certain molecular bonds, the field inside a nucleon is not perfectly contained at the nucleon's surface. At very short distances, when two nucleons are pressed close together, the fields from their interiors begin to overlap. The constituents inside one nucleon begin to feel, weakly and indirectly, the field activity inside the neighbouring nucleon. This overlap produces an effective attraction between nucleons. It is not a new force appearing from nowhere. It is the residual effect of the primary field leaking slightly beyond the nucleon's boundary when nucleons are in direct proximity. The force between nucleons is therefore a secondary consequence of the primary field that binds their interiors, in the same way that the forces between neutral molecules are secondary consequences of the electrical fields operating inside them. This reframing matters for the question of what the nucleus is made of. The glue holding the nucleus together is not a separate interaction added on top of the nucleon structure. It emerges from the same field responsible for confinement inside each nucleon. The nucleus coheres because the primary binding field inside each nucleon is strong enough and active enough that even its residual effects at the nucleon surface are sufficient to overcome electrical repulsion between protons. The residual nature of the internucleon force also explains several of its properties directly. Its short range follows from the fact that the leakage of the primary field beyond the nucleon boundary drops away rapidly with distance. The primary field is so effective at confining its effects within the nucleon that only immediate neighbors feel any significant residual interaction. Its relative weakness compared to the primary field follows from the same logic. What reaches between nucleons is a fraction of what operates inside them. This means the nucleus has a hierarchical structure of binding. At the deepest level, constituents are bound inside nucleons by a primary field of extraordinary strength. At the next level, nucleons are bound inside the nucleus by a residual effect of that same field, operating at a fraction of its full intensity. The nucleus is held together by an echo of the force that holds its own components together, and that hierarchy, two nested levels of confinement, producing two nested levels of binding, is what the final structural picture of the nucleus must account for completely. Everything that has been established now fits into a single coherent picture, and that picture has a specific shape. The nucleus is not one level of structure, it is two levels of confinement nested inside each other, each one producing the conditions that make the next one possible. At the innermost level, three constituents are bound inside each nucleon by a field that strengthens with distance, stores energy in its own activity, and makes isolation of any single constituent physically impossible. This confinement is absolute. It produces most of the nucleon's mass from field energy and motion, rather than from the mass of the constituents themselves. It defines the nucleon as a stable, persistent object with a fixed charge, a fixed mass, and a fixed set of quantum properties. The nucleon exists because this innermost confinement holds. At the outer level, nucleons are bound inside the nucleus by the residual effect of that same field leaking between neighboring nucleons at close range. This confinement is less absolute. Nucleons can be removed from a nucleus if enough energy is supplied, unlike constituents which cannot be removed from nucleons under any conditions. But within the nucleus, the residual binding is strong enough to hold protons together against their electrical repulsion, to organize nucleons into quantum energy levels, and to produce a stable composite object with its own distinct mass, charge, and quantum identity. Each level of confinement produces something the level above it depends on. The inner confinement produces nucleons. The outer confinement produces nuclei. Remove the inner confinement and nucleons dissolve, taking the nucleus with them. Remove the outer confinement and the nucleus disperses into free nucleons, which themselves remain intact, because the inner confinement continues independently. This nested structure means the nucleus has properties that cannot be understood by examining either level in isolation. The mass of the nucleus depends on the mass of its nucleons, which depends on the energy of their internal confinement. The binding energy of the nucleus depends on how nucleons interact through their residual field effects, which depends on the properties of the primary field operating inside them. The charge of the nucleus comes from the charges of its protons, which come from how the fractional charges of their internal constituents add together. At every point, The outer level inherits its properties from the inner one. The nucleus is not built on top of nucleons the way a structure is built on a foundation. It is more intimate than that. The nucleus is what the inner confinement produces when multiple instances of it are pressed close enough together for their residual effects to matter. The nucleus emerges from nucleons the way nucleons emerge from their constituents, as the natural consequence of a field organizing matter under confinement into the only stable configuration the rules allow. This also means that the identity of the nucleus is distributed across both levels simultaneously. A carbon nucleus is carbon not simply because it contains 6 protons, but because those 6 protons each contain specific internal configurations of constituents whose combined charges produce the proton charge, whose confinement produces the proton mass, and whose residual field effects produce the binding that holds 6 of them together in the specific quantum arrangement that defines carbon. What the nucleus is made of then cannot be answered by naming one level of this structure. Naming only nucleons misses the confinement that produces them. Naming only the constituents misses the residual binding that organizes them into nuclei. The complete answer requires holding both levels together as a single nested system where each layer is the necessary precondition for the one above it. With 2 nested levels of confinement established, something subtle becomes visible that the previous layers were building toward without naming directly. The nucleus does not have a fixed internal arrangement in the way a crystal has a fixed lattice. Its protons and neutrons do not sit at defined positions waiting to be located. They occupy quantum states, and quantum states are not positions. They are probability distributions spread across the entire nuclear volume simultaneously. Each nucleon inside the nucleus exists as a smeared presence. Its position at any given moment is not defined until an interaction forces a definite outcome. Before that interaction, the nucleon genuinely occupies a range of locations within the nucleus, weighted by the probabilities its quantum state assigns to each region. This is not a statement about measurement difficulty. It is a statement about what the nucleon's physical situation actually is between interactions. The same applies to the constituents inside each nucleon. Their positions within the nucleon are similarly distributed, governed by the quantum state of the nucleon's interior. At any moment, the constituent is not at a specific point. It inhabits a region, with certain locations more probable than others, and the distribution of that inhabitation is what the confinement field shapes and maintains. This means the nucleus, examined at full depth, is not a collection of objects arranged in space. It is a nested set of overlapping probability distributions, each shaped by the forces and quantum rules operating at its level. The protons and neutrons are distributions within the nuclear volume. The constituents are distributions within each nucleon. The fields binding each level are themselves quantum fields, meaning they too exist as distributions of possible configurations rather than fixed structures. What this does to the concept of identity is significant. A proton inside a nucleus is not simply a proton sitting in a particular place doing a particular thing. Its quantum state is entangled with the states of the other nucleons around it. The energy levels it occupies are defined relative to the entire nuclear system, not independently. In a precise sense, the proton inside a nucleus is not quite the same object as a free proton in empty space, because its quantum state is shaped by its participation in the nuclear system as a whole. This distributed identity has measurable consequences. The precise energy levels available to nucleons inside a nucleus differ from those of free nucleons because the nuclear environment modifies the effective forces each nucleon experiences. The binding energy of the nucleus reflects not just how strongly nucleons attract one another, but how their quantum states overlap and interact across the entire nuclear volume. The nucleus is a genuinely collective quantum object, not an assembly of independent parts. The constituents inside nucleons are subject to the same collective behavior at their level. Their quantum states inside a nucleon bound within a nucleus are subtly different from their states inside a free nucleon, because the nuclear environment reaches inward and modifies the boundary conditions the nucleon experiences. The two levels of confinement are not perfectly isolated from each other. They communicate through the quantum states they share. The nucleus is therefore not made of parts in any classical sense of that word. It is made of quantum states organized across two nested levels of confinement, each level shaping the states available at the other, and the whole system existing as a single interconnected quantum object whose properties emerge from all of it simultaneously. And this brings the final layer into view, where the question of what the nucleus is made of resolves into its most precise and complete answer. Quantum states do not exist on their own. They are states of something. The distributed, nested, collectively organized structure described in the previous layer is not floating in abstract mathematical space. It is grounded in physical fields that permeate the nuclear volume and extend, in diminishing form, beyond it. The nucleus is made of quantum states, and those quantum states are states of fields. Fields are the final substrate. At the innermost level, the field binding the constituents inside each nucleon fills the nucleon's interior completely. It is not located between the constituents like mortar between bricks. It occupies the same space the constituents occupy, interacting with them continuously, carrying momentum between them, and storing energy in its own configuration. The constituents and the field are not two separate things sharing a volume. They are aspects of the same physical system, each defined partly by the other's presence. This field is a quantum field, meaning it does not have a single definite configuration at any moment. It exists in a superposition of possible configurations, and its actual state is the quantum state of those possibilities, weighted by their respective probabilities. When the field interacts with something, a specific outcome is selected from that distribution. Between interactions, the field genuinely inhabits multiple configurations simultaneously, and the energy of that superposition contributes to the mass and binding of the nucleon. The electromagnetic field occupies the same nuclear volume and operates on the protons within it. It does not bind the nucleus, but it shapes the energy levels available to protons by adding a repulsive contribution that the binding field must overcome. The quantum state of the nucleus reflects the balance between these two fields at every point in the nuclear volume, with the binding field winning at short range and the electromagnetic field becoming relatively more significant as the nucleus grows larger. Between nucleons, the residual effect of the binding field acts as a further quantum field mediating the internucleon interaction. This residual field is itself quantized, meaning the interactions it mediates happen in discrete exchanges rather than as a continuous classical force. Each exchange carries momentum and energy between nucleons, and the cumulative effect of these exchanges produces the effective attraction that holds the nucleus together. The binding between nucleons is therefore not a steady pull, but a rapid, continuous series of quantum events maintaining an average cohesion. The nucleus as a whole sits in a quantum state that is the combined state of all these fields simultaneously. The binding field inside each nucleon, the electromagnetic field acting on protons, the residual internucleon field, and the quantum states of the constituents and nucleons themselves are not separate ingredients added together. They are aspects of a single unified quantum configuration that the nucleus occupies at any given moment. Changing the nucleus means changing this configuration. Adding a neutron introduces a new set of quantum states that must be accommodated within the existing field structure. Removing a proton alters the electromagnetic contribution and shifts the balance of the binding field's residual effects. A nucleus in an excited state occupies a higher energy configuration of the same fields, and when it relaxes to its ground state, the energy difference is released as radiation, which is itself a quantum of the electromagnetic field propagating outward. Every observable property of the nucleus, its mass, its charge, its spin, its stability, its size, its response to external fields, emerges from the configuration of these nested quantum fields and the states they organize. The nucleus is not made of particles that happen to be described by fields. It is made of fields that organize themselves under the rules of quantum physics and the constraints of confinement into the stable, persistent composite structure we call a nucleus. The question has traveled far enough inward that the answer can now be stated without remainder. The nucleus is made of quantized field configurations organized across two nested levels of confinement, producing stable composite structures whose properties emerge entirely from the fields, the forces, and the quantum rules operating within them. At the surface of the answer, the nucleus contains protons and neutrons. This remains true and remains useful. It correctly identifies the freely existing objects whose interactions define nuclear chemistry, radioactive behavior, and the chart of stable elements. For most purposes, this level of description is sufficient and accurate, but the question asked what the nucleus is made of according to quantum physics, and quantum physics does not stop at the Nucleon surface. Inside each proton and neutron, three constituents move within a confinement so absolute that no experiment has ever extracted one freely, and no experiment consistent with the known rules of physics ever could. Those constituents account for a small fraction of the nucleon's mass. The rest comes from the energy of their motion under confinement, and from the energy stored in the field that binds them, a field that strengthens rather than weakens as separation increases, and that converts any attempt at extraction into new matter before isolation can occur. That field is a quantum field. It exists in superposition. It carries momentum between constituents in discrete exchanges. It stores energy in its own configuration. It makes the nucleon heavy not by containing heavy pieces, but by maintaining an interior of such energetic intensity that the whole system weighs far more than its parts. The nucleon's mass is mostly made of confinement. The nucleus then binds these nucleons through the residual leakage of that same field at the nucleon surface, an echo of the primary interaction that is nonetheless strong enough to hold protons together against their electrical repulsion. This residual binding organizes the nucleons into quantum energy levels, governed by rules that forbid two identical particles from sharing a state. The nucleus fills those levels from the lowest upward, producing shell structures, preferred compositions, and measurable stability patterns that reflect the underlying quantum organization directly. The identity of the nucleus is distributed across both levels simultaneously. Its mass reflects confinement energy at the inner level and binding energy at the outer level. Its charge reflects how fractional constituent charges add within each proton. Its spin reflects how nucleon spins combine across the occupied energy levels. Its stability reflects whether the quantum states available at both levels produce a configuration that has no energetically accessible pathway to change. Across all of this, the fields are primary. The constituents are excitations of fields. The nucleons are bound states of those excitations. The nucleus is a bound state of those bound states. Each level of structure is the field organizing itself under confinement into the only stable configuration the quantum rules permit at that scale. There are no solid pieces at the bottom of this description. There is no irreducible particle sitting at the center of everything waiting to be named. There are fields, and there are the states those fields are allowed to occupy, and the nucleus is what those states look like when two levels of them are nested together and held in place by forces that have never, in the entire history of the observable universe, been observed to fail. The weight of everything you have ever touched comes from this. The stability of every atom in every object in every room you have ever entered rests on two nested confinements, each one absolute within its domain, each one producing the conditions that make the other meaningful. The nucleus persists, not because it is rigid or impenetrable, but because the quantum rules governing its fields allow no other outcome under ordinary conditions. And so the nucleus, examined all the way down, turns out to be made of something that has no everyday name and no everyday analogy that fully captures it. It is made of organized field energy, constrained by quantum rules, arranged by confinement into layers of stable structure, and held there by forces whose properties make stability not a fragile achievement, but a natural consequence of how fields behave when matter is compressed to the smallest scales the universe permits.